Hello and welcome to our webinar on arcs of circles. This is 10.2. This video is to be watched before 4/8, I believe. That is Friday, and make sure you guys watch this because this is what we're going to be doing in class on Friday. Our first thing that we have to do is, for our in, is foil these together, and we talked about this in the previous lesson in 10.1. There were two methods you could do. You could foil it, which is what they're suggesting here, or we could use the box method. So I'll go through both of them again just so you remember, and I believe these are the same problems. But the foil method F stands for first, so we multiply the first terms together. There's our F, and so we take r times r, which gives us r squared. Then we take our outside terms, which would be the guys furthest away from each other, and so we multiply r times 14 plus, so we add on plus 14r. Then the I stands for the inside terms, the two terms closest to each other, and so we'd multiply those together, which will give us 14r, and then we multiply our last terms together, which are the ones that are at the end of each parenthesis, which all of this ends up spelling out FOIL, and so 14 times 14, I believe, is 196, and so if we combine our like terms, our final answer for this one should be r squared plus 28r plus 196. Now, you could also use the area model that we talked about in the previous one, and that's what this foil down here was trying to help you remember. The area model, remember, you just draw a rectangle that looks like this and divide it up into 4 squares, and one side is r plus 14. The other side is also r plus 14 in this case, and so we just find the area of each little square and then combine them together to get our final answer. So the length of the height of this side is 4, the width is r, or the height of this side is r, the width is r, so r times r is r squared, and then height is r, width is 14, so we combine those, we get 14r. We have 14 a height now and a width of r, so we get another 14r, and last but not least we have a height of 14 and a width of 14, which gives us 196. So if we combine all of those like terms, basically we're combining this diagonal and leaving these guys alone, and we should end up, when we combine them, end up back to that. So that's another way of thinking of FOIL, either the area model or the FOIL method. So you need to know how to do this as we go along. So then we have a whole bunch of definitions that we got to talk about, and this is always the fun part because you guys get to copy these down. So please, I would highly suggest, if you haven't already, go back and print out the PDF file of this, and then it makes it much easier to copy down these because they're blank, and it just makes it much easier. So in a plane, an angle whose vertex is at the center of the circle is considered a central angle. So if we have our vertex of our angle is at the center of the circle, we have a central angle, and so ADB in this case is the central angle, and that's what we were telling you up there. If the measure of the central angle is less than 180 degrees, the arc, which is the outside on the circle, is considered a minor arc. So it is smaller than 180 degrees, we get a minor arc. If it's greater than 180 degrees, that's this next one, that's a major arc. And major arcs are usually labeled by 3 letters. Minor arcs are usually labeled by 2 letters. So I'm going to put little arc symbols above them. There, you notice they're curved. That represents that they're arcs. So we have a major arc, A, C, B, and they'll tell you which way. If you're going to use a major arc, they'll tell you which direction to go. I'm going from A to C to B, so that's my major arc. And then if the endpoints of the arc are on a diameter, then we have a semicircle. And so semicircle is the only one, is only 180 degrees, because if you look at the definitions, it's less than 180, more than 180, and a semicircle happens when you end up with a central angle of 180 degrees. So that's really where we're going. The measure of the minor arc can be defined by its central angle, and major arc also. So if you notice, if I ask you for the measure of the minor arc GF, we have 60 degrees because that's the measure of the central angle. And then the major arc is the difference between 360 degrees and whatever we're dealing with angle-wise. So if I wanted to find the measure of the major arc GEF, which is basically what's left over of my whole circle from the minor arc, then you notice I'm going from G to E to F. When I do that, then I would take 360 and subtract away the minor arc, which is 60 degrees, to get the major arc length of 300 degrees. So that's how we find major arcs, minor arcs. They're all off of the central angles. So then we also, just like we had segment addition way back when, where you could add two segments together to get a third larger segment, we can do the same with arcs. We can add arc AB, this arc over here, plus arc BC, which would be the arc down below, to get a major arc of ABC. And usually we should have little arc symbols above these guys here to represent that they're arcs. So that's what we're talking about. So you can add two arcs together to make a third larger arc, and that's really what the arc addition postulate's all about. So then we get to go into some wonderful other definitions. So we have two arcs of the same circle are congruent if their arcs are congruent. So if we have two arcs on the same circle or congruent circles, then their arcs are congruent if they have the same measure. So basically what we're saying is if we can somehow determine that the arcs are the same measure, then and the circles are congruent, the arcs are congruent. So in the same circle, this is theorem number one, so in the same circle, the two minor arcs are congruent if and only if their corresponding chords are congruent. So basically what we're saying here is that we could say that arc AB, which is this arc right here, arc AB, is congruent to arc BC. Those would be congruent if and only if we could say that chord AB, which we just label as a segment, is congruent to chord BC. And that's really all we're talking about. So that's what that theorem is. And then of course this next one is talking about the diameter, and it says if the diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So you'll notice here's my diameter that is perpendicular to the chord DF. So the first thing I would say is DF and EF are perpendicular. Then I now know that this thing not only bisects the arcs, but it also bisects the chords. So the chord, there's two things we could write here. We could write that segment ED is congruent to segment EF, or we also know that DG, arc DG, is congruent to arc GF. So there's really two things that come out of it. I think they want the arc one in this one, but both of them, the chords are also the same thing. All right, so then we move along to our next one, and this guy's a little bit off, so I'm going to see if I can get the picture in better focus. So if one chord is perpendicular to the bisector of another chord, then the first chord is a diameter. So they're saying if we have any chord and we have another chord that is perpendicular to it and cut in its perpendicular bisector, then the chord is a diameter. The perpendicular bisector is the diameter. So in this case, JK is the diameter of the circle. And finally, our final theorem, and I think this is the final thing that we have to copy down and take our time on, so you probably need to pause these as we're going along. But in the same circle or congruent circles, two chords are congruent if and only if they're equidistant from the center. And so over here on the drawing, we always measure distance at a 90-degree angle, so these guys have to be the same length. So EF, if EF is congruent to EG, then we know segment chord AB is congruent to chord CD. And we'll move this over just a little bit. So that's really what we're talking about in this case. We're just trying to represent that if the chords are, we can say if the chords are congruent, then we know the distance from the center is the same, or we can say if the distance from the center is the same, then the chords are congruent. We can go either way on that. That's what the if and only if is all about. So then we get to go along and we have some practice problems that we're going to do. So please try these on your own and then pause it, and then we will I will go through the answers of these. But we're going to name arc PQ. It's either minor arc, major arc, semicircle, or we don't know. So looking at PQ, PQ looks like is up here, is this arc right here. And looking at that arc, is that arc less than 180 degrees or more than 180 degrees? Well, if it's less than 180 degrees, then it is a minor arc, and that's really all we're talking about. In this one, it says Kn and Jl are diameters. So Kn, this length right here, and Jl are diameters. Find the indicated measure. So we want the measure of arc LNK. So let me mark LNK. Ln, whoa, that goes all the way around over here. LNK. That's what it's telling me. So I got to find the length of that arc. Well, I know that this thing, I know that from N to K is 180 degrees. I know that for a fact. All right, so that's 180 degrees. So N to K is 180 degrees. I also know that this is 55. It's just what's the measure of this one? Well, we also know that NK is 180 degrees down below down here. So to find the missing piece, I have to subtract 60 and 55 from 180. And so if I take 180 and subtract 60, then subtract 55, that'll tell me what's left over, which is 65 degrees in here. And knowing that's 65 degrees, so 65, 55, and then the 180 will give me the length of L and K. So 65 plus 55 plus 180 will be my total length, and that's arc is 300 degrees. And we could have done it even easier. I worked it on the hard way. Sorry about that. You probably are sitting there going, why is he doing it this way? I probably could have just done, well, I'm only missing this piece of the circle, since it would have been all the way around as 360 degrees. I could have just subtracted 60 and gotten the 300 degrees. So yeah, good afterthought there. So the next question is, what is the measure of angle JQN? So JQN is this angle right here. So we're looking for the measure of this angle, and they told us that KN and JL are diameters. So they're nice straight lines. They're not kind of crooked or anything like that. It's not like real close to a straight line and a little bit of an angle. So those are being straight lines. Two straight lines cross. This is a theorem that this is the very first theorem that we learned in this class. And hopefully you remember it. When there are two angles across from each other, hopefully you remember that vertical angles are congruent. So JQN must be a vertical angle. So now we're asking for what is the measure of arc JN. And so we're looking for this arc right here. We just said this angle is 60 degrees from the previous problem. So what's the measure, since the central angle is 60 degrees? What's the measure of the arc? Well, hopefully you can see it's also 60 degrees. Now we're going to find the measure